So don't forget. Okay. Whatever. Okay. Does everyone have the packet? Do you know where to find the packet? It's the event. Yeah. All right. So midterm 3. So as a reminder, this is the second half of chapter 16. So we did strong acid calculations on midterm 2. So midterm 3 is about weak acids, weak bases, their conjugates, properties of salts, Lewis acids, those things, and then all of chapter 17. So chapter 17 was buffers, titrations, what else? KSP, those types of things. All right. So I will point out midterm 3 is a difficult midterm. This is probably the hardest midterm in terms of material and scope out of all 4 midterms. The 4th one is the easiest. Okay. Make sure that you have the supplemental information, your calculator. This is a calculator heavy chapter or midterm. And then the key. I forgot my key, so I'll have to do the math. But I'll point out that I actually have a copy of the supplemental information at the bottom here. Those are your constants. But I mean, at this point, you should know what KW is. Here's the quadratic formula, but will you ever have to use it on the exam? No. Percent ionization, and then that is your buffer calculation. But here, notice that this Henderson-Hasselbalch equation, pH equals pKa plus log base over acid. Can it be whatever base and whatever acid you want? No, it has to be your conjugate base, conjugate acid base pair. So A minus over HA, or it can be base over its conjugate acid HB plus, right? This is especially important for titrations because what you're adding is not directly the conjugate, but you're actually adding directly a strong acid or strong base to neutralize a weak system to make the conjugate in situ. Right. And of course, it's given in concentrations, but you can also use millimoles as well. All right. So what chapter do you want to start with? We just want to go in order. What? 17? 17. Okay. So let's do 17. Yeah, 17's a doozy. Okay. So let's calculate the pH of the following solutions. Assume always 25 degrees Celsius. That's important because that means we know that Kw is equal to 1 times 10 to the negative 14. For all of these, right? That's important because Kw is equal to Ka times Kb for a conjugate acid-base pair. That's very important. Okay, so let's calculate the pH of mixing. What are we mixing? 100 milliliters of acetic acid and 5 grams of sodium acetate. So I give you the molar mass of sodium acetate, and I give you the Ka of acetic acid. So hopefully you know by now the pKa of acetic acid is what? 4.774, yeah. But remember, to get that pKa, you just take negative log of 1.8 times 10 to the negative 5, and it gets you that pKa, right? So what are we mixing together? Acetic acid is a weak acid. How do you know? I gave you a Ka, so that is HA. What is sodium acetate? What are you adding? Is it its conjugate? It is its conjugate. So sodium acetate is NaA. So this is a buffer. We're using the Henderson-Hasselbalch equation. pH equals pKa plus log base over acid. Specifically, I mentioned that base over acid has to be the mole amount or concentration of A minus over how much HA you have. So you are adding these amounts directly. So you just need to convert these into mole amounts and plug it into the Henderson-Hasselbalch equation because you are adding the acid and its conjugate base directly. So let's go ahead and do that. So HA, 100 times 0.2, that is what, 20? No, yeah, 20 millimoles of HA, right? So I know that the denominator is 20 millimoles, and then 5 grams of sodium acetate. So I'm going to use the molar mass to get that into moles. So 5 grams of NaA, and I tell you the molar mass is 82. So 82 is 1 mole of NaA. And then we got to be careful. We need to make sure that our mole units match. So 5 divided by 82.03 is 0.0609 moles. So I think that is 60.9 millimoles of NaA. And these are the numbers that go into our Henderson-Hasselbalch. pKa is 4.74 plus log base 60.9 over 20. So 60.9 millimoles of NaA and then 20 millimoles of acetic acid, HA. And that equals something. I forgot my key. Log 4.74 plus, whoops, 4.74 plus that number is 5.22. That's the pH I got, right? But the hard part is getting that base to acid ratio and recognizing that what you are adding is an acid and its conjugate base directly. So those values go straight into the Henderson-Hasselbalch. Notice I kept everything in millimoles because they're both in the same volume. They're both in 100 milliliters of liquid. So it's not necessary to divide 100 by both of them. All right, next one. We are mixing pyridine and pyridinium chloride in 500 milliliters. So pyridine is a base. It is a base. How do I know? I give you the Kb of pyridine. So if pyridine is a base, what is pyridinium chloride? It's its conjugate, yeah. So pyridinium chloride, chloride is Cl minus. So I have a Hb plus thing over here. So that is a base and its conjugate acid directly. So we also can use those values straight into the Henderson-Hasselbalch equation. But we're not going to do 5 over 5. We got to convert both of those into mole amounts first. So that's the hard part. So 5 grams of pyridine. I give you the molar mass of pyridine is 79.1. So 1 mole. So that's the base. And then 5 grams of pyridinium chloride. That has a molar mass of 115.6 grams. Is 1 mole, and that is Hb plus, that's pyridinium. And so those values are 0.0632 moles of the base component, and then 5 divided by 115.6 is 0.0432 moles of pyridinium. So this is Hb plus, right? So notice that this is a buffer. We're going to use the Henderson-Hasselbalch equation. I give you a Kb. So negative log of that number, 1.7 E negative 9. Okay, so this is equal to 8.77, I believe. But this is pKb. I need pKa. So if I take 14 minus that, I get that the pKa is 5.23. This is the number that I want to use. That's the number I want to use, right? Because the Henderson-Hasselbalch is pKa plus log base over acid. So we got to convert that pKb to pKa. Those two numbers add up to 14. So putting this all together, pH equals 5.23 plus log base over acid. So that means I'm putting pyridine up top, 0.0632. This is pyridine. And then the bottom one is pyridinium. So I'm going to put 0.0432 on the bottom, and then you get your answer. I'm not going to write it. Okay. Yeah. Did I put? Oh, yeah. You should have said that earlier. Should have said that earlier. Okay. Whatever. Boop. Whatever. No, that's fine. This meeting. Okay. There we go. Yes. Yeah, that would be super annoying. Okay. Good. All right. That one. All right. Next one. 50 milliliters of acetic acid and 5 milliliters of sodium hydroxide. This is a buffer again. But am I going to put those millimoles straight into the Henderson-Hasselbalch? No, I'm not. So let's get those millimole amounts. So acetic acid, 50 times 0.2. Is that 10? 10 millimoles of acetic acid. So that's HA. But I am adding, so 0.2 times 5, I think that's 1. 1 millimole of sodium hydroxide. Remember, your base to acid ratio is the amount of A minus over HA. So I need to figure out how much A minus is in my solution. I'm mixing a weak acid and a strong base. So I make A minus by that addition of strong base. So the reaction that's happening is HA is combining with sodium hydroxide to make A minus and water. So what's happening is a full-blown chemical reaction. So you need to write out a BCA table, but the numbers are easy here. Notice you're starting with 10 millimoles of acetic acid, 1 millimole of hydroxide. So that means hydroxide's limiting you, -1, -1, +1. After this neutralization reaction, you have 9 millimoles of HA, and you have 1 millimole of A minus. Those are the two numbers that go into your Henderson-Hasselbalch equation. It is 1/9. But you know 50% of your classmates are going to put 1/10 because they just see a base, they see an acid, and they shove it into the Henderson-Hasselbalch. But that base to acid ratio is not whatever base and acid you want. No, it has to be the acid-base conjugate pair. You make the conjugate base by the addition of sodium hydroxide where you consume some of that weak acid. So the pH calculation is going to be pH equals pKa. So this is acetic acid. So 4.74 plus log base over acid. So it's 1/9, whatever that answer is, right? Okay, so yeah, okay, so then the next one. What if we mix together 50 milliliters acetic acid and 5 milliliters of HCl? Is that a buffer? Think about what you're mixing together. HCl is an acid. Acetic acid is also an acid. So how will we calculate the pH of this? The strongest, yes. So we can actually just ignore the acetic acid component. All right, but we still need to figure out, we can't just say, oh, the pH is negative log 0.2. We can't say that. We can't say that because we're mixing together HCl and acetic acid. So HCl is actually being diluted a little bit. So we need to figure out what is the H plus concentration in the mixture. All right, so we have 1 millimole of HCl here, and we're mixing it with 50 milliliters of stuff. So what is the total volume? It is 55 milliliters. So we are still diluting that H plus. So we need to figure out what that new concentration is. It's not 0.2. So 1 millimole of HCl is being diluted to a total of 55 milliliters. So this is the new concentration of HCl because you're only adding like a little bit into a pretty large volume. So this HCl concentration is 0.0181 molarity. And so this is a strong acid. So you can just simply negative log that number. So the pH is 1.74. Right. So this one's a little bit tricky, okay? That yes, you recognize it's two acids. Just take the strongest one, where the strongest one's a strong acid, but you are diluting it because you're mixing it with something else. And you can just treat that something else like water, right? And so the reason we can ignore acetic acid only contributes a little bit of H plus. And because pHs are on a logarithm scale, the place value that acetic acid actually changes is way out there. And so because of that logarithm scale, the strongest acid wins here. Okay, so yeah, the tricky thing here is that HCl is diluted in the process. We can't just do negative log 0.2. Okay, next one. Let's mix together pyridine and HCl. Pyridine is a base. HCl is a strong acid. Right, so I'll go ahead and get millimoles. So 40 times 0.12 or so 1.5, there is 6 millimoles of base. And then how much is that? 1.5 millimoles of HCl. So will my Henderson-Hasselbalch be 6 over 1.5? No. A reaction happens first. I hope at this point, chapter 17 homework was due. You've done enough BCA tables and titrations to recognize how the BCA table ends up. Everything's just a 1-to-1 ratio. So after these two things mix, so this is what I call my lazy BCA table, where I just write the after line, because I recognize adding a strong acid to a base neutralizes it. So I should only have 4.5 millimoles of base left over. In that process, I've converted all of that base that I've consumed with HCl to make its conjugate acid. So this is 1.5 millimoles of HB plus when these two things react with one another. You consume 1.5 of this to make 1.5 of the conjugate acid. This is the ratio that you put into the Henderson-Hasselbalch equation. So did we already get the pKa of pyridine before? Yeah, 5.23. So that means the pH is equal to 5.23 plus log base over acid. So 4.5 over 1.5. But 50% of your classmates will just put 6 over 1.5. You can't do that. A reaction happens first, and then your answer is something. Okay, great. So notice, basically, anytime you add a strong acid to something to neutralize it, you have to do that BCA table first. You can't just shove those numbers straight into the Henderson-Hasselbalch. Okay, so this one, we are adding 40 milliliters of pyridinium chloride. I think this is 6 millimoles. But pyridinium chloride is what? Is that a base? Nope, that is a conjugate acid of a base. So this is actually BH plus. That's BH plus, pyridinium chloride. In the previous question, I said pyridine. This one's pyridinium chloride, so it's BH plus. And then I'm adding sodium hydroxide. So I think this is 1.5 again, 1.5 millimoles of strong base. Can I just put those things straight into the Henderson-Hasselbalch? Nope, you got to neutralize them first. So that means after, so this is my lazy BCA, where I just write the after line. How much BH plus do I have left? 4.5 millimoles, or HB plus, whatever, same thing. So that's your acid component in the Henderson-Hasselbalch equation. And then that means, since you've added base, you've neutralized this weak acid to a weak base, that's where you make B. So we have 1.5 of that base left, or made, because we neutralized it. And so this is the base component. All right. So notice that this one's very similar to the previous one. The previous one, I started with the base and I added strong acid and then shoved it in the Henderson-Hasselbalch. Here, I'm starting with the weak acid. I'm adding strong base to get back a little bit of the weak base. I'm still going to use the same Henderson-Hasselbalch equation. pH is pKa, what is it? 5.23 plus log base over acid. So it's 1.5 over 4.5 equals something. You could look up the key. Okay. All right, so those are all like acid-base weak system. So let's look at something else. So here we are mixing HCl and sodium hydroxide. I give you no Kas, I give you no Kbs. Why? They're all strong. So really, it's just a BCA table, no Henderson-Hasselbalch. So I'm going to just get those millimole amounts. So 40 times 0.25, there is 10 millimoles of HCl, 45 times 0.25. There is 11.25 millimoles of sodium hydroxide, right? So after these two things react, what is in excess? Sodium hydroxide. By how much? 1.25 millimoles. And that is what's going to dictate our pH, whatever is in excess. That all 10 millimoles of HCl reacted with 10 millimoles of sodium hydroxide to make a pH neutral salt, NaCl, right? So we just need to figure out the concentration of that. So the concentration after this neutralization is 1.25 millimoles. of the hydroxide over the total volume of the entire mixture, so 95 milliliters. So 1.25 divided by 95. The hydroxide concentration here is 0.0132 molarity. And so if you negative log that, you get POH. So negative log that number, I get 1.88. So then to get the pH, subtract from 14, and you get 12.12. Sure. All right. So yeah, by overshooting your, pH by a little bit here, yeah, that pH is going to be super, super, super basic. At the equivalence point, it's a pH of 7. But yeah, once something is in excess, that pH skyrockets because now a strong something is in excess. Okay, so let's keep going. So those were all our buffers, recognizing what am I adding to the beaker. There are 2 ways. So let me just review. 2 ways to make a buffer, right? The first way is you add HA and A- directly. You have to look closely at the formula. Look really closely at the formulas and stuff. If you add HA and A- or B and HB+ directly into your beaker, you just use the Henderson-Hasselbalch. That's it. You go straight to Henderson-Hasselbalch. But then the second way you can make a buffer is you can start with HA, but then you add sodium hydroxide, something strong. So in this case, you actually have to BCA first, then Henderson-Hasselbalch. That's the difference, right? Or conversely, you could start with a base and add HCl, same idea. You have to BCA first, then Henderson-Hasselbalch, because you're adding something strong. And so those are the 2 ways to make a buffer. So let's go a little bit backwards here. Here, I'm asking you, you want to prepare an acetic acid sodium acetate buffer with this pH. This is your target pH. How many moles of sodium acetate should you add to 0.25 moles of acetic acid? So think about what you're adding to your beaker. You start with acetic acid and you're adding acetate. So what kind of buffer are you making? The first type or the second type? The first type. So we don't have to do any BCA table, all right? So we will delete that. We're doing a type 1 buffer where it goes straight into the Henderson-Hasselbalch. So the idea here is I give you that target pH. So let me just write pH equals pKa plus log base over acid. I tell you the amount of acid you start with. We know the pKa, we know the pH. We're solving for how much base do you have to add. So simply 4.85, equals the pKa, 4.74 plus log. I'll just calculate the full base over acid ratio first. So I think this is 0.11 equals log base over acid. So to undo that logarithm, take both sides to the 10. So 10 to the negative, or no, 0.11. So that base to acid ratio equals 1.29. So what that means is for every 1 equivalence of acid, you need 1.3 equivalences of base. So that means if I start with 0.25 moles of HA, then I need 1 to 1.29 equivalences of the base. In this case, it's A-, so times 0.25. So I need to add 0.322 moles of sodium acetate to make this buffer, right? You can check your work by getting the base to acid ratio with these numbers. So 0.322 over 0.25 and plug that into Henderson-Hasselbalch, and hopefully you get your target pH back of 4.85, right? So that's how you make a buffer with just adding the acid and its conjugate base directly. But remember, you don't have to do it that way. In this one, you want to prepare the same buffer. You want to prepare that acetic acid sodium acetate buffer with that target pH, 4.85 again. So that's my target. But this time I'm asking how many moles of not sodium acetate, but look, sodium hydroxide should I add, right? So this one's different. This one's different. This is a type 2 buffer. So notice that in the previous one, we simply, got the base to acid ratio, figured out how much acetate we need. But this one's a little bit different. The target pH is the exact same. So I know that my base to acid ratio still needs to be 1.29 over 1. But the problem is a little bit different because here, this is a type 2 buffer where I'm adding sodium hydroxide. So remember, you always have to do a BCA table before you plug it into Henderson-Hasselbalch. So if you start with your acid and you add hydroxide, that's how you make your conjugate base. So if this were, a different pH buffer calculation, you would have said, oh, okay, you start with 0.250 moles of acid. You're going to add some random amount of base. All of that base gets consumed and you make an N amount of some random amount of A minus. So that means after this reaction happens, you lose a little bit of HA. That's your HA amount. And you gain a little bit of A minus. And so this is what you want to put into that base to acid ratio. All right. We already got the base to acid ratio is 1.3 over 1. So what I'm going to say is 1.29 over 1. That's my base to acid equals base is N. Acid is 0.25 minus N. So notice that the process is different because we started with a BCA table. So base is N over 0.25 minus N. And that N amount is the mole amount of strong base, sodium hydroxide, you need to add. So this one is a little bit different. In our previous question, we just set this equal to, okay, 2.50. How much base do we need? Okay, but in this one, since we're adding base, we have this plus N minus N factor. And so you solve for N. I don't know what it is. So what you'll do is you'll cross multiply. So you get N equals 1.29 times 0.25 minus N. So 1.29 times 0.25. So N equals 0.3225 minus 1.29 N. So moving some stuff around, you get 2.29 N equals 0.322. So you get N equals 2.29. 0.151408 moles of sodium hydroxide is required, right? So this is a type 2 buffer where you do a BCA first. That one is definitely harder than the previous one, all right? Okay, and you can check yourself. You can just change the wording of the question. Say, oh, you mix together 0.2408 moles of sodium hydroxide and 0.25 moles of acetic acid. What is the pH? You'll do your BCA table first, then your Henderson-Hasselbalch, and hopefully you get that target pH of 4.84. Let me just quickly check that that answer is right. Let's see, is that answer right? 0.141, is that what I said? Yeah, 0.141. Okay, good. All right, so that's how you make a buffer. And so in these last two, it was backwards thinking. I gave you the target pH. I wanted you to tell me how much I needed. In all the other ones, I just give you amounts and you calculate the pH. So it's a little bit different. All right, so these questions. So, a buffer resists pH change because once you have large amounts of your acid and conjugate base, if you add a little bit of strong acid, all it goes is into doing your BCA table and changing that base to acid ratio. So which of these buffers is most resistant to pH changes? So both of them are acetic acid. Here we have 500 milliliters of a dilute acid base combo or 500 milliliters of a more concentrated acetic acid sodium acetate buffer. It's the concentrated one that has a larger buffering capacity. I did that demo earlier, remember? Right, that like with pure water, if I put a tiny bit of acid in, color changed drastically, right? while I had a dilute and a stronger buffer, the dilute buffer, it could take on a couple drops, like one squirt before it really changed color, but the really concentrated buffer took a couple squirts in order for it to change color. The reason is because of the BCA table. So pretend like, you know, I had HA, I added base, and I made the, you know, the conjugate base or whatever. All right, 50 times 0.1. We think about it. We are starting with 50 millimole and 50 millimole of the acid-base conjugate pair. Pretend I add, you know, 10 millimoles of hydroxide. When you do the after line, you end up with 40 millimoles of HA and 10 millimoles, or no, sorry, 40, yeah, millimoles of HA and 60 millimoles of A minus. Calculate the new base to acid ratio. It changes a little bit. But think about answer B, where, oh, it's still like the same like 1-to-1 buffer ratio, but it's more concentrated. Notice when you do the BCA table, HA plus hydroxide gives you A minus. Our before line is not 50, it's actually 500. So if you add the same amount of base here and you do the subtraction, you're left with 490 millimoles of HA and 510 millimoles of A minus. Calculate the new base to acid ratio. It barely moves away from 1. So that's the idea, that if you start with more moles of junk, when you add a little bit of strong base or add a little bit of strong acid, the numbers in your before line are larger. So it takes more strong acid or strong base to drastically change that base to acid ratio, right? Okay, so that's buffering capacity. Has to do with either concentration, mole amounts, or even volume. Okay, so which of these 3 titrations are going to have the highest or most basic pH at the equivalence point? All right, so I have 3 titrations. The first one is between a strong acid, strong base. Here's HF and a strong base, and here is what is that? Hypochlorous acid and a strong base. So notice here, these acids are what's in your Erlenmeyer flask, and then you're dropping sodium hydroxide in from your burette. I'm not asking you what is the pH at the beginning of your titration. I'm asking you, what is your pH when you're at that equivalence point? That's what I'm asking. So at your equivalence point, is HCl present at your equivalence point for this first one? No. When these 2 things react, it produces sodium chloride. That is what's present at your equivalence point. At your equivalence point, you've completely neutralized HF. What is present at the equivalence point in this second titration? Not HF, it's actually NaF or F minus, whatever. Okay, that is what's present at your equivalence point when you fully neutralize that weak acid to its conjugate. Or here, this one, what is your product when you neutralize this weak acid? It is not that acid, it's actually NaClO minus or whatever. So notice that we're not inspecting the acid. We are looking at the conjugate base. That is what's present here at your equivalence point. You start with HA, but at your equivalence point, you have A minus. So really, this question is asking which of those conjugate bases are the most basic, right? So the first one, do you know what the pH is at the equivalence point for this first one? It's 7, yeah, because NaCl is pH 7. So we are comparing NaF and NaClO. We need to figure out which one's more basic. How would we do that? If we know their KBs, right? Do we know their KBs? Not directly, okay, not directly, but I give you the Kas for their acids. So let's look at these acids. Okay, HF versus HClO. HF is the stronger acid, so therefore NaF is going to be the what? Weaker base. Yeah, so here the Kb for NaClO is about 10 to the negative, I don't know, 6. But for NaF, Kb is equal to 10 to the negative 10. So we see that NaClO is the stronger base. All right, so that's the tricky part, recognizing at the equivalence point, it's not the acid that's present, it's the conjugate that's present. So we have to look at the Kas or whatever to identify, what substance am I trying to use to calculate that pH? Okay, so this one, which of these titrations has the highest, most basic pH at the halfway to the equivalence point? So I'm not asking you what's the pH at the equivalence point. I'm asking you, what's the pH right here? What's special about the halfway equivalence point? pH equals what? pKa, yeah. So that's where your answer is. Look, here are your Ka values. You simply just calculate what is the pKa of both of these acids. So the pKa for that first one is about 10 to the negative, or no, so it's about 4. Doesn't really matter what the number is. It's like 4 point something. And then the second one, its pKa is 8 point something. So that means B is going to have the most basic pH. All right. Okay, good. That's conceptual. Recognizing that even without the math, you don't even have to do the math, right? It's all about just comparing Kas or Kbs depending on what's being asked. Okay. All right, so that is titrations. Henderson-Hasselbalch. You only have a buffer sometimes, just in this region. At the beginning of your titration, it's just a weak acid. At the equivalence point, it's just a conjugate, it's its weak base. And after the equivalence point, it's just a strong base in excess. Okay, so we also talked about KSP in terms of molar solubility and dissolving stuff in water, right? It's why some things are more soluble in water than others. It's because they have different KSP values. So let's order these substances in order of increasing molar solubility. So this is X. Molar solubility is X in your ICE table when you do a KSP expression. This is in the unit of molarity. So the idea here is KSP represents a certain type of reaction. It's when this AB solid dissolves in water, what comes out of it. So you can write this as, okay, AB solid, drop it in water, you get a little bit of A plus and a little bit of B minus. So the KSP for this reaction is just like all Ks, is the concentration of A plus times the concentration of B minus at equilibrium. Solids do not go into the equilibrium expression. But to calculate molar solubility, we have to do an ICE table where we drop a random amount of solid in there. We lose a little bit of it. We gain an X amount of A and an X amount of B. So now I'm putting KSP in terms of molar solubility when it actually dissolves. So at equilibrium, we have N minus X of your solid, X amount of A, and X amount of B. So put those X's in the KSP. So we see that KSP equals X squared. And I tell you this is 1 times 10 to the negative 10. So I think therefore X molar solubility is 1 times 10 to the negative 5 molarity. So that means if I have a liter of water, or if I drop AB solid into water and make a saturated solution, the concentration of the compound that actually dissolves should only be 1 times 10 to the negative 5. That's what it means. That's the limit. That's like, the saturated concentration. So we do the same things with these other things, except notice that the stoichiometry is going to be a little bit different. So notice that KSP expressions follow a very systematic way. And then to get your KSP in terms of molar solubility is also follows a trend. So if you think about how does AC2 dissolve into water, you get an A2 plus cation, but you get 2 C minuses. So when you do your ICE table, you should gain an X amount of A, but a 2X amount of C. And that's where this one differs. So when we put this into the KSP expression, this one is still, the expression itself is still A plus, times C minus, but it is squared. Don't forget the 2 there. I know we took away the squares for a while, or the stoichiometry for a while with weak acids, weak bases, but it comes back for KSP. Then to put your KSP in terms of molar solubility, this is where we put in those X's. So KSP is equal to X times 2X squared, or if you simplify this, this is 4X cubed, and is equal to that 1 times 10 to the negative 8. And so if you solve for that, you get that the molar solubility, this one is a little bit different. 1e negative 8 divided by 4 to the 1/3. This one, X is equal to 1.4 times 10 to the negative 3 molarity. So that one has a larger molar solubility, more of it dissolves. And now the last one, hopefully you can just figure this out without doing the ice table. All right. AD3 dissolves in water. You gain an X amount of A, but then how much D? 3X. So when you put this into the KSP expression, KSP is going to be equal to the A cation concentration times the D concentration, but it is cubed. So then you put this in terms of molar solubility X, 3X cubed. I think 3 cubed is 24. So this is equal to 27. 27X to the 4th equals 1 times 10 to the negative 15. Solve for X. So 1e negative 15 divided by 27 to the 1/4 is equal to 7.8 times 10 to the negative 5. There we go. Whoops, molarity. So I think that one is more soluble than A, but not as soluble as B. All right, so that's kind of interesting because if you look at this KSP for this third one, it has the smallest value of KSP. So if you just simply order it, oh, it's going to go B, A, then C, just based upon KSPs, you won't be right because we have to solve for the X component in terms of molar solubility. So I think in terms here, solubility in increasing, the least soluble is actually that A compound, then it's C, then it's B, if we rank it in terms of the X. So you can't just use KSP solely because the stoichiometry is different in all of them, right? So that's how you do molar solubility. And if these examples are in pure water, we're dropping these solids into pure water. So we can do that X analysis there. All right, so this one, 14, we are dissolving something, but not necessarily in pure water. So what we see here is I give you the KSP of calcium hydroxide is that. I'm asking you, what is the molar solubility of this thing? Not in pure water, but we're going to buffer it to a concentrate or to a pH of 11.5. So notice here, if we write the KSP expression for this compound, it's going to be calcium 2+ times the hydroxide concentration, but it is squared. I'm telling you via the pH what the hydroxide concentration is, right? Where if pH is 11.5, that means the POH is 2.5. So that means that the hydroxide concentration at equilibrium in that KSP expression is equal to 10 to the negative 2.5 molarity, whatever that is. So I am telling you how much hydroxide there is already. So you need to tell me how much calcium, what's the maximum amount of calcium I can add to then equal the KSP that's given. So notice that I give you KSP, I give you hydroxide via the pH. So you just solve for how much calcium do I need. So putting that all together, 6.5 times 10 to the negative 6. How much calcium can I put in there? Then the hydroxide is what's 10 to the negative 2.5. This is equal to 0.00316, but it is squared. And so you just solve for that. So square that, 6.5 e to the negative 6 divided by that. I get that the maximum amount of calcium you can have in this solution at this buffered pH of 11.5 is equal to 0.65 molarity. So the hint is here is that when I give you a pH, I'm telling you how much hydroxide there is in the KSP expression, right? Okay, so a little bit more in chapter 17. Oh, not that much more. Okay, so we looked at solubility trends, all right? We did KSP or whatever. It in itself is an ice table. And so there's ways that we could affect the solubility of things. Because if we just think of, a generic KSP expression, M2 plus or aqueous plus X minus 2 minus aqueous. So this is a KSP expression that if you put MX in pure water, only a set amount of ions are produced based upon the value of KSP. We can affect solubility in the extent how much solid is produced if we do a couple things. We can either do the common ion effect, where the common ion effect, so common ion always decreases solubility, and so it always decreases X. Adding acid usually increases solubility if your anion is a base. And then the last one is KF formation usually increases solubility. So that's the trend, but it only works sometimes. So here, common ion effect says, oh, I can dissolve MX in pure water, but if I dissolve this salt in something that already has M2 plus or already has X2 plus, then this thing is less soluble. The reason is you just think Le Chatelier's principle. Add M2 plus, you shift the reaction backwards. More solid is produced, your thing is less soluble. So here, if we add HCl to a saturated solution of NaCl, is that an example of the common ion effect? Yes, because adding HCl adds Cl minus, it pushes it backwards. But you might think, oh, HCl is an acid, that's not common ion. But what I'm not actually focusing on that H plus, I'm actually focusing on the Cl that you're adding, not the acid. Okay, what if I add sodium nitrate to NaCl? Is that an example of the common ion? Yeah, so same KSP. So here, adding sodium nitrate adds sodium plus. You're adding another common ion. So that one also is common ion. What about adding HBr to NaCl? Nope, because there are no common ions in HBr. And you can tell, because if you just think about the solubility of NaCl, it includes the Na plus cation, Cl minus anion. Okay. All right, so let's keep going. So then which would be an example of a pH dependence on solubility? Remember that adding acid usually increases the solubility of your solid, but only if your anion is a base, because acids react with bases. So just like Le Chatelier, if you neutralize X, you remove X anion from the reaction, it shifts your reaction forward. So if X is a base and can react with acids, it's going to be affected by pH dependence. So adding HCl to a saturated calcium hydroxide. Calcium hydroxide is basic, so this will become more soluble in acidic conditions. Adding acid to ammonium chloride, will that do anything? It will not, because ammonium is an acid, chloride is a pH neutral salt. So this is not a basic salt. So it does nothing to that. After I told my cat story, someone emailed me and they were like, I have gout. You know what gout is? Yeah. It's a disease where I think I had to Google it because I had no idea. And it's the buildup of uric acid in your joints. And so you have typically very inflamed, painful joints all the time. I had to Google it. And they were asking, they're like, I heard you feed your cat vinegar to make, the solid more soluble so they can excrete it out. Will that work on my gout? And I was like, well, I'm not a doctor. And I was like, well, I'm not that kind of doctor, but I looked it up. So uric acid is already an acid. So it's the buildup of this solid uric acid in your joints. So do you think, just based upon what we are talking about right now, will adding acid affect the solubility of uric acid? No, it won't. So the problem with that system and gout, unfortunately, is that uric acid is already an acid and a solid. And so that's unfortunate that no, my simple cat cure with just, feeding her vinegar, it helped her because struvite was a basic salt and became more soluble in acidic conditions. But unfortunately, gout can't. So I just said, follow your physician's guidance. I'm not that kind of doctor, but I appreciated their application of the concepts to things that relate to them. So yeah, adding HCl to something that's acidic ain't gonna do nothing. But if we add HBr to calcium carbonate, will it do something? Yes, it will, because carbonate is basic. Adding HBr to calcium bromide will do anything? In terms of pH dependence. It's not going to do anything for pH dependence, no, because this is a neutral salt, but it is going to make it less soluble because this one's actually common ion. But that wasn't the question. That wasn't the question. This one's actually common ion. Okay. So do make sure you look at that. So in the previous one, we were looking at common ions. This one, we're just looking at acid. Okay. And then this final one, yeah, adding HCl to saturated calcium chloride, same thing. This is pH neutral, so it's not going to do anything. This is actually another example of common ion. All right. So yeah, adding acid to things that are, it's only going to affect things that are basic. And actually on that, let's just do number 18 then. Which solids from this list are going to become more soluble in acidic conditions? So what kind of salts are we looking for? Basic ones, that's it. So iron chloride. So just, yeah, no. So let's make it a chapter 16 question. Are these salts acidic, basic, or neutral when they dissolve in water? Iron chloride is going to be what? Acidic, because of the iron 3+ is a Lewis acid. Calcium cyanide. It's going to be basic because cyanide is the conjugate of HCN, which is a weak acid. So this one is going to be affected by pH changes. Okay, silver fluoride. This one is actually, we can't answer that one because silver is an acid. It's a Lewis acid, and fluoride is a base. So technically, I don't know whether it's going to be acidic or basic. Probably my key says it's basic because of the fluoride, but I'm actually not sure. I think F- would be a stronger base than silver plus is as a Lewis acid, but I'm not sure. That's not a good question. I would not give that one on the exam. What happens when I write my own thing? Okay, the next one, lead chloride. This one, not going to do anything. It's going to be pH neutral. Or I guess is lead a Lewis acid? Not sure. I'm not sure if lead's a Lewis acid, but the idea here is that chloride is pH neutral, so it's not going to do anything, right? Calcium hydroxide, absolutely going to be affected by pH changes because you have a strong base as a anion. Super basic. Strontium perchlorate is pH neutral, so it is not affected by pH changes because perchlorate is a neutral anion. Magnesium phosphate, is that going to be affected by pH changes? Yes, because phosphate is a base. That is the generic formula of struvite, the cat crystal, the bladder crystals my cat had. I think people can get it too. You don't drink enough water, right? Yeah, it's that phosphate, super basic, because phosphoric acid is a weak acid and you've already taken 3 protons off of it. So it's absolutely going to act like a base. And then the last one, aluminum hydroxide, that's also going to be basic because of those hydroxides, also affected by pH changes. Cool, cool, cool. Perfect. All right. So that was, looking at salts and seeing that, oh, the basic ones are the ones that are affected by pH changes. And so the very last topic we looked at for factors in solubility was the complex ion. So this is KF. So which of these would be examples of complex ion affecting solubility? So typically when you add something that can make a complex ion, it increases molar solubility. But that's if you make something that is a complex ion. Complex ions are ions, they are aqueous. Because the idea is if you, again, have your KSP expression, right? If you're able to consume this metal, so with pH effects, adding acid usually reacts with the anion, removing the anion, pushing the reaction forward. Complex ion removes the metal instead to make a complex ion, and again, pushes the reaction forward, so you dissolve more solid. So here, adding sodium hydroxide to aluminum consumes that aluminum to make, look, a complex ion. How do I know it's a complex ion? It's ionic and it's aqueous. So this has a KF. So this first one is an example of formation, complex ion formation affecting solubility, because we're adding something to form a complex ion. But here, look at the second one. See how it's worded a little bit differently? We're still adding sodium hydroxide to aluminum, but this time, are we forming a complex ion? We are not. We are forming aluminum hydroxide. So this one is not an example of complex ion, because this is not a complex ion. All right, we're making something else. Specifically, we're making a solid. So keep going, adding HCN to saturated iron to form a iron cyanide complex. So we're forming a complex. So this is absolutely an example of complex ion formation improving solubility, because we are adding something that makes a complex, a aqueous ionic complex. And then the last one, just forming iron 3 oxide. This would not be an example of complex ion 1, because this is not a complex ion. The idea is it needs to be ionic, it needs to be aqueous. You add a little bit of a ligand to make these complex ions. So there are two examples here: the aluminum with the 4 hydroxides anion, and the iron with 6 cyanides, and it's 3 minus, right? So this one is not a complex ion. Okay, perfect. All right, so that is all of chapter 17. So yeah, there's very little, again, equations on the supplemental information. So let's go back to chapter 16 and finish those up, because the one that we didn't use yet is percent ionization. So I want us to look at that real quick. Okay. So remember, a buffer is a mixture of HA and A minus, or a base and its conjugate acid. Chapter 16, we just looked at one of these things. What if you just have HA in solution? What if you just have A minus in solution? So it's all about, you know, can you recognize what's in solution, which K to use? So here, I have a solution of a weak acid, and it has a pH of 2. What is the Ka of this acid? So this is one type of, you know, Ka ice table I can give you. But remember, with ice tables, there are 2 types of ice tables. One where I give you K and you solve for X, and you have to do you have to do an approximation. But this one, I don't give you Ka. I want you to calculate Ka. This is a type 1 ice table where I give you hints at the ice table. I give you hints at the entire table so you can fill it all out and calculate Ka. So there's no approximation here that we need to do. So the strategy here is we have a weak acid, we have a Ka, so why don't we just write a generic Ka expression? HA dissolves into water to get H plus and A minus. That's the chemical equilibrium happening, right? Write out your ice table. I tell you this is a 0.12 molarity solution. Zeros of that, we know that this reaction must go forward. So plus X, minus X, plus X, plus X. So at equilibrium, we have 0.12 minus X over, and then X amounts of the other things. So if we write our Ka expression, which is H plus times A minus over HA, we can tell through the equilibrium line that Ka is equal to x squared over 0.12 minus x. What a lot of students will do right now, because we're really good at it, is get rid of that minus x. But we're not going to do that, because what piece of information did we not use yet? The pH. The pH is x. Well, similar. It's almost x. So if that's the pH, that means the H plus concentration at equilibrium is equal to what, 10 to the negative 2? This is equal to x. X is equal to 0.01 molarity. I told you that through the pH. This is equal to x. So why would you get rid of the x in the denominator if we know what x is? All we have to do is plug that number in, right? So when you do that, right, plug that x in both of those places. So the answer, Ka, is equal to 0.01 squared over 0.12 minus 0.01. Notice how 0.01, x is actually a pretty big number. It's almost 10% of the concentration. So let me just show you, if you did make the approximation, when you don't have to, what your answer will be. And you know I'm going to have both options there, if you make the approximation or not. So the answer, 0.01 squared over, oh fudge, I hate this calculator, 0.01 squared, okay, divided by 0.11. So my answer is 9.1 times 10 to the negative 4. Let's say you approximated when you didn't have to. So you just did x squared. So if you just do 0.01 squared over 0.12, you get 0.12. 8.3 times 10 to the negative 4. So you get a different answer, right? I'm going to have both on there. Okay, you do not need to approximate. I tell you what x is. Don't be lazy. You just plug it back in. Okay, all right, so there's that one. That's the type 1 type of ice table where I'm asking you Ka. All of the questions that I ask you the pH, yes, that you absolutely make an approximation there. That's a type 2 ice table. Okay, so let's look at these two substances. We got docwinic acid, so it's a fake weak acid, and then winonia, which is a weak base. I know because I give you a Ka and a Kb. All right, so what is the pH of a 0.3 molarity docwinic acid solution? So docwinic acid is an acid. So we're going to use the Ka. Did I give you the Ka of docwinic acid? Yes, I did. Perfect. So when we do this, this is a type 2 ice table where, okay, docwinic acid's an acid. So you put HLO into solution, you get H plus and LO minus out. If we start with 0.3 minus x plus x plus x, Ka equals x squared over 0.3 minus x equals 1 times 10 to the negative 5. That's the Ka I give you. But I don't want to do the quadratic, so I will just get rid of that minus x and solve for x. So all this became was x squared over the initial concentration equals Ka, because I gave you Ka for that weak acid. So if you do that, 1e negative 5 times 0.3, take the square root, you get x equals 0.00173 molarity, but it's the molarity of what? H plus, because we used Ka. And so if you negative log that, you get a pH of 2.76. You put an acid in solution, it should be acidic. Oh, what, just scroll up. What did I do? Okay. Here we go. Perfect. Okay, so next one. So I gave you HA's Ka, you put HA in solution. Here, what is the pH of a 0.3 sodium docwinate solution? What is that? Is that an acid? It is a conjugate base. Notice that I have sodium plus and LO minus. That is a weak base. That's the conjugate of the weak acid. So if this is a base, I need to use Kb. But did I give you Kb? Did I give you Kb of docwinic, or sorry, did I give you the Kb of doquinate. No, I gave you a KB of winonia. That's something else. So how am I going to get the KB of doquinate? I'm going to use Ka. All right. So remember, for a acid-base conjugate pair, HLO has a Ka of 1 times 10 to the negative 5. LO minus is a base. It has a Kb of Kw over Ka. So its Kb is 1 times 10 to the negative 9. All right. So that is the Kb that we want to use. That is of the conjugate base. So notice I put the conjugate base into solution. I need to use a Kb. I get that Kb from Ka. So when we do the ice table, we will end up x squared over 0.3 again. When we use the approximation, we want to set that equal to Kb because doquinate is a base, but we got that from Kw over Ka. We know Ka, we know Kw. All right, so we solve for x. Kb, I think was, what did I say? Times 1 times 10 to the negative 9. I try to make the numbers easy so we don't have to do calculator stuff all the time. 1e negative 9 times 0.3, take the square root. So this answer x is 1.73 times 10 to the negative 5, but this is the molarity of what? Hydroxide, because we used Kb. So that means the POH is equal to negative log of that, 4.76. So that means the pH is equal to 14 minus that, 9.24. We put a base into solution. What should the pH be? Basic. Is it? Yes. Perfect. Okay. Keep going. What is the pH of a winonia solution? That's a base. Did I give you the Kb of winonia? I did. So simply x squared over 0.3 equals Kb. And I give you Kb, 1 times 10 to the negative 10. Perfect. Solve for x. Okay, so that is a, yes, the base, and I give it to you. All right, 1e negative 10 over times 0.3, take the square root of that. I get x is 5.48 times 10 to the negative 6. Molarity of what? OH minus, yes, because we used Kb. So that means POH is equal to something 5.26, and then that means the pH is equal to something else, 8.74. Again, you put a base into solution, it should be basic. I gave you just like the winonia, if you squint your eyes, it looks like ammonia. That's it, it's ammonia. All right, okay, so then what is the pH of a 0.3 winonium chloride? Is that a base? That is a acid. So winonia is composed of HW plus and Cl minus. This is analogous to NH4 plus. That is a weak acid. So that means I have to use Ka, but I didn't give you the Ka of winonium, but you can get it from the Kb of winonia. So the idea here is ammonium. So let's see, winonia is W. So that has a Kb of 1 times 10 to the negative 10. So that means winonium, HW plus, has a Ka of 1 times 10 to the negative 4. Because these two multiplied together have to equal Kw. All right. This is what I'm putting into solution, HW plus, the acid. So when you solve for the ice table, you get x squared over 0.3 equals Ka, because winonium is an acid. That is equal to 1 times 10 to the negative 4. So 1e negative 4 times 0.3, take the square root. X is equal to 0.0055 molarity, and this is the concentration of H plus because you used Ka. So this is negative log of that is pH equals 2.26. You put an acid in solution, it should be acidic, right? There are 4 different things you can put into water. You can put in HA, a weak acid. Just use the Ka that's given, equals x squared over whatever concentration. But I can give you an example where it's not HA, it could be NAA. NAA is the conjugate. So you need to use KB, but KB comes from KW over KA. It's still X squared over initial concentration, but X is hydroxide concentration, right? So those are two scenarios I could give you, two different ones, or I can give you a base. I'll give you KB, and it's simply X squared over initial concentration. Or I can give you its conjugate, HB chloride. So that's HB plus. You have to use Ka, but calculate it from Kw. So equals X squared over whatever. Those are the four different things I can give you, either the straight up acid or base or the conjugates. Four different scenarios. Know which one it is. Okay, keep going. All right. So given this information, I give you a Ka for docwinic acid, a Kb for winonia. Tell me, is the salt, winonium docwinate, is it acidic, basic, or neutral when you dissolve it in water? So what we know is that, okay, the conjugate of a weak acid is a weak base. The conjugate of a weak base is a weak acid. So I'm not combining HLO and W. I'm actually combining HW plus, I'm combining LO minus, that's a base, and I'm combining HW plus, that is an acid. Because you might be looking at this and being like, oh, docwinate is a stronger acid than winonia is a base, but that's not what I'm mixing together in solution. I'm putting as a salt the conjugate acid and the conjugate base. So I need to see which one is LO minus a better acid than HW plus is, or sorry, is LO minus a better base than HW plus is an acid. So we don't want to compare this Ka to this Kb. I need to convert this Ka for docwinic acid because I'm putting its conjugate base into solution. The Kb for this is 1 times 10 to the negative 9. And the Ka for winonium, the conjugate acid, it's not 1 times 10 to the 1 times 10 to the negative 10. It's 1 times 10 to the negative 4. So we see that HW plus is the stronger substance. It's the stronger acid, or it's like, yeah, it's stronger. So in this case, HWLO is going to be acidic because the acid part is a stronger acid than the base part. But remember, we are not comparing the acid and base directly. We're actually comparing the conjugates instead, right? So I could go back here. Look, winonium chloride has a pH of 2.26. That's fairly acidic. If you look at the same concentration of sodium docwinate, it's the pH is 9.24. This 9 is much closer to 7. It's more closer to pH neutral than the conjugate acid is what we see here. And so since they're in equal concentrations, we can simply just compare the Kas to the Kbs, but make sure you compare the right ones. Okay, I want to do one more. Tell me. Okay, I have a diprotic acid, H2A. If I tell you that Ka1 is equal to 1 times 10 to the negative 3, and then Ka2 has a Ka2 of 1 times 10 to the negative 9. If you put NaHA into solution, is this going to be acidic or basic? So I have a diprotic acid, has 2 protons, and I take them off one at a time. So if you notice, if you think about this, all right, you start with H2A, very, very similar. We want to know which one's stronger, the acid, the acidic part of this substance, so HA minus, can act as an acid or a base. We need to figure out which one's stronger. We think about it, okay, H2A can lose 1 proton to make HA minus. It can lose another proton to make A2 minus. This is Ka1 and 2. So Ka1 is 1 times 10 to the negative 3. Ka2 is 1 times 10 to the negative 9. Now let's think about the conjugates, all right? So if we work backwards, when A2 minus gains a proton, when it acts like a base, this is Kb1. This is equal to 1 times 10 to the negative 5. How do I know that? Ka2 and Kb1 have to multiply to give Kw because it's the same acid-base conjugate pair. When Ha minus acts as a base, what is its Kb? 1 times 10 to the negative 11. Yes, negative 11. Okay. Because of, yeah, so this is Kb2. All right, so now how can we answer this question? Is Ha minus going to act as an acid or base? So we want to start here. I'm not putting H2A in water. I'm not putting A2 minus in water. If you put H2A in water, it's obvious. It's going to be acidic. There's only a Ka. If you put A2 minus in water, it's pretty obvious. It's going to be basic because it only has a Kb value pointing away from it. But look at Ha minus. Look, it has a acid value and a base value. But notice how I'm only choosing, I have to choose the correct Kas and Kbs. I'm selecting Ka2 and Kb2 because these are the only arrows pointing away from it where Ha minus is a reactant. So based upon these numbers, is Ha minus going to act as a base or an acid? Based upon the numbers. Base. No. Acid. Yeah, acid, because this is the bigger number. So yeah, Ha minus, because Ka2 is larger than Kb2, this thing is going to act as an acid. Right? So that one's trickier, where, yeah, I have a diprotic acid, but I'm putting a substance that can act as both an acid or base, but I need to choose the correct one. This one I would say is a little bit harder than this one, but see how it's very similar. I'm not looking at the straight up Ka and Kb's given, I'm actually looking at the conjugates. And that's similar to how if we have a diprotic acid. Okay. Okay, so just a couple more. All right, so let's keep going. I need to delete this so I have room. All right, so let's look at some conceptual things. Okay, consider two hypothetical acids, HL and HN. They're both weak acids because I give you Kas. So which acid is more acidic, HL or HN? It's going to be HL because this Ka is larger, much larger. But then which one's more basic? It's going to be NaN because its Kb is much larger. We could go ahead and just fill in what the Kas and Kbs are. So if HL has a Ka of 1 times 10 to the negative 3, L minus should have a Kb of 1 times 10 to the negative 11. N minus should have a Kb of 1 times 10 to the negative 8. So we see, yeah, that the Kb of N minus is much larger. So it's going to be more basic. Remember last midterm, stronger the acid, crappier the base. It's because of that Ka-Kb relationship to Kw. The larger Ka is, the smaller Kb has to be. So if you have an acid that's a really bad acid, its conjugate's going to be a fairly good base. All right. Which solution is more ionized at equilibrium? So we had an equation, percent ionization is equal to the H plus concentration over the initial acid concentration times 100. So that's how we calculate percent ionization, right? So for both of these solutions, isn't the denominator the same? But where they differ is what the numerator can be. So what we see is that HL is going to be more ionized because H plus is a larger number for that percent. You could calculate it, but you don't have to. Recognize that I give you two options that have the same denominator, the same concentration, but the one that's more acidic, the one that has the larger Ka value has the larger numerator. So it's going to be more ionized in solution since the denominators are the same. Right? So yeah, Yeah. Okay. So then which one is the more stable conjugate base? So I should have put that right there after which one is more basic. So what we see is that the more basic thing is the less stable conjugate base. So when you have a anion that's really stable, it doesn't want a proton. It acts as a very, very poor base. So what we see is that L minus, because it's not very basic, doesn't need a proton to make it more stable. That N minus is not so stable, is not as stable. So it's more likely to gain a proton. So what we see here is that the stronger acid HL makes a more stable conjugate base because it's very likely that that proton comes off because L minus is very stable. HN, on the other hand, is not a very good acid that once it donates that proton, what's left behind isn't very stable and wants that proton back. So that's that idea of, acid base duality in terms of conjugates in relation to Kw. All right. Okay, so more stable conjugate base. So basically, the less stable an anion is, the better base it's going to be because it's going to want that proton to stabilize it. All right, and the final one here, which solution is more ionized at equilibrium? So same idea, we're going to use this percent ionization equation, but it's a little bit different. Here I say, oh, you have a 0.1 molarity HL solution and a 0.01 molarity still an HL solution. So these are the same acid. They're the same acid. Okay, but their concentrations are different. One's more dilute. So let's just think mathematically. In which situation, a big number or a small number in the denominator, does the percentage come out to be large? Think about it. Small, yeah. So here, lower concentration things actually are more ionized. And it's because you're putting a smaller number in that denominator when you do this calculation. Both of them are going to have similar acidities. But here, what we see is because the magnitudes of their concentration are really different, the percent ionization actually increases for very, very dilute solutions. All right. Okay. Okay. All right. So if you do if a question says to, calculate percent ionization, just do it as if you were calculating the pH of the solution. And once you solve for X in your ICE table, so X squared equals, whatever equals Ka, X is equal to the H plus concentration, right? So like instead of me asking you what is the pH, I can ask you what is the percent ionization, and so the calculation at the very end is a little bit different. The same strategy still applies. Okay, so 3 more and then we're done. Okay, so but we already know how to do this one, right? Predict whether these salts are acidic, basic, or neutral. So remember, we're looking at conjugates. Okay, the cation and anion forms of weak acids and weak bases. So we need to split all of these into cations and anions and predict, okay, is it going to be neutral, acidic, or basic? The idea is if it comes from a weak thing, like a weak acid, its conjugate is a weak base. If it comes from a weak base, its conjugate is a weak acid. But if it comes from something strong, then it's pH neutral. So common pH neutral cations are group 1 and 2 metals. Common pH neutral anions are anything that comes from strong acids except sulfate. So I guess I can just write them down. So pH neutral cations include like potassium, sodium, calcium, strontium, magnesium, all of those things, groups like 1A and 2A. pH neutral anions come from any strong acid. So chloride, bromide, iodide, nitrate, what else? Chlorate and perchlorate. Am I missing one? No, that's it. Yeah, 6 of them. Because you might think sulfate, but this is actually a weak base. So So that's the exception. So those are your pH neutral anions. If those show up in any formula, all it means is you can ignore it. It's pH neutral. You ignore it, right? Any of these. So that means KClO4. Both of these are one of the pH neutral ones. So this is going to be pH neutral. It's going to be pH 7. The next one, ammonium nitrate. We have NH4 plus and nitrate. Which one of those ions can we ignore? Nitrate, because it comes from nitric acid. It's a pH neutral salt. But ammonium is a acid because it comes from ammonia, a weak base. All right. Potassium acetate. So we have K plus and CH3COO minus. That K plus is pH neutral. This thing is a base because it comes from acetic acid. Iron nitrate. What thing can we ignore? Nitrate. Iron is a what? Acid. Perfect. Aluminum bromide. What thing can we ignore? Bromide, because it's Br minus. Al3 plus is an acid. It's a Lewis acid. Highly, basically, yeah, any like metals that aren't these pH neutral ones are going to be a little bit acidic. Ki, neutral. Yep, you can ignore both of them. Yeah, K plus and I minus are both pH neutral. Calcium fluoride. Calcium you can ignore, but it's the fluoride. F minus is actually a base because HF is a weak acid. All right, and then the last one here, this thing and a chloride. What can we ignore? Chloride. So the other thing it's attached to must be a acid. Yes, it is an acid. It basically is NH4 plus. Or you can think, oh, it's a cation because it's attached to an anion, a chloride anion. The other thing has to be a cation, and cations are usually acids. Okay. All right, last two, and then we're done. Okay, so we have a structure. It's glycolic acid, a highly water-soluble alpha hydroxy acid. That's a popular chemical skincare exfoliant. This is different than salicylic acid, which is a beta hydroxy acid. So out there in the skincare community, I'm into that. AHAs versus BHAs, all right? Okay, so glycolic acid is highly water soluble, and it's an AHA, alpha hydroxy acid. So I'm asking you, which of the indicated protons is more acidic? Acids donate protons. So if you think in which scenario, when you rip off that proton, if whatever is left behind is very stable, then it's very likely that proton's going to be ripped off. So what we see here is we have two options. We can either rip off this proton, right, off of that oxygen, but what's left behind is this negative charge on an oxygen. Or we can rip off this proton and we're left with a negative charge on that oxygen. So you might be thinking, oh, we're leaving a negative charge on an oxygen in both cases. So they're the same acidity, but that's not true. What's special about one of these negative charges on the oxygen? What's special about one of them? One of them can undergo what kind of phenomena? Resonance, and that's this one, right? So proton number 2 is more acidic because when that proton leaves, what's left behind is something that's very stable. A carboxylate group that is stabilized by resonance versus that oxygen, there's no resonance. Okay, so that negative charge is highly localized in one spot versus in this one, we can delocalize that negative charge, spread it out so it's not as, like densely charged, and we stabilize it. All right, so based upon that answer, okay, we say this proton is more acidic. So then if I drew this molecule, okay, then what spot then is more basic? Spot 1 or 2? Spot 1 is more basic. Yeah, so this is more basic. For the same reason as the whole idea of conjugates being opposites of one another. The better the acid, the crappier its conjugate base. So if this carboxylic acid group is very acidic, then its conjugate, the carboxylate, is a really bad base. Or here, this alcohol group is a really crappy acid. So its conjugate is going to be a very good base. Or you can think about it like this. Remember, more acidic something is, the more stable the conjugate base left behind. So here, this is very unstable. That negative charge on that oxygen, super unstable. So we can stabilize it by one of those lone pairs grabbing a proton, making it charge neutral. That's how you stabilize it. Versus this guy, this negative charge hanging out on this carboxylate, super stable. It doesn't need a proton. It's stable on its own. So it's going to act as a very, very bad base. So see how our answers changed when we looked at the conjugates. Okay. All right, because bases are things that you can think, accept protons or donate electrons. Because which of these followings is the last one, is the most basic? Bases either accept protons, or you can think about Lewis bases, same definitions, can either donate electrons. They can do either. Because when we look at these three compounds, only one of these can act as a base. It'll help you if you draw them. This is NH4. This is CH4. And this is water. I didn't draw any of the hydrogens because I don't feel like it. All right. So a lot of students, they'll think when I say, okay, which one's the most basic? They'll circle this one because it looks the most like ammonia. But NH4 plus is a what? It's an acid. Yes. They're confusing with NH3, but they're like, oh, it looks close enough. But no, there's a big difference. If you draw the structure of ammonium, can this thing, here, I should put the charge, accept any hydrogens, or can it donate any electrons? It can't. In order to accept a proton, it has to donate electrons. There are no lone pairs on that nitrogen. This is never going to act like a base. Versus CH4. Can this thing act like a base? No, there are no electrons to be donated. That this carbon atom's never going to accept more hydrogens than it needs. But then this last one, can this act like a base? Water. It can. There are electrons there. And when water does act like a base, what does it become? It becomes H3O+. Is that something that you've seen before? It is. So H2O is the only thing here that can act like a base, which is weird because we think, oh, water's neutral. Like, it's not a base. It's neutral. But the other things absolutely cannot act like bases because there are no electrons to be donated. Okay, so that's it. Best of luck. I'll stay behind. I think that's it, right? Yeah, we finished the whole packet. So I'll post this online. Do all practice exams. Do all of them. Yeah.